So this is the Postgres DBA Accelerator. It's an exercise in teaching people a little more about Postgres. The training material comes from a set of open source stuff that we use in the Postgres community for introducing people to Postgres absolutely from scratch. So web developers or sysads or that sort of thing. So we are going to pick a few bits of that material because I'm presuming that everyone who is at this event at least has some basic database concepts. We don't have to, really start from the bottom. We're just going to get into what some of the more interesting bits are, and maybe some of the things that people migrating from other database engines, may need to know a little bit about. So we're going to do a little bit of the block one, which for those who are actually working through the hands-on stuff, is just how to set up those hands-on environments. It's based on the Docker image for PostGIS with a couple of other little bits added into it. Then a little bit of the Postgres DBA basics section, just a little bit around some of the command line tools, for people who are coming from other engines to get a bit more familiar with that. And then most of it will be around the troubleshooting and the query tuning. We have a small group. Anyone has a question, just ask. This isn't a big enough bunch that we need to keep everything very structured. For those who are, those who are following along with the hands-on, the repo is hosted by Snowflake's Labs, and all the various bits for Docker Compose and the URLs for downloading the sample code are in there. So if everyone could get that cloned, we can have a look at setting up the demo environments for those who are following along. So just out of interest, who is following along? What? You're not? No. Fine. No, just asking. Just asking. Okay, so it's not zero. Fine. Let's go. Cool. All right. Cool. Have you managed to get it cloned?
Yes.
All right. So then, are you a Docker user or a Podman user?
Podman.
Okay. So I've got mine running on Podman as well, and just replace Docker with Podman, and it works this far. One of the images is fairly large. Right. Yeah, I've also got my Podman in a VM because this is an Ubuntu 22.04, which is upgraded from a 20.04. So a bunch of the network CNI stuff doesn't work. So just a nice clean new 24.04 VM. Everything just came up nicely under Podman. Yeah, right. Sorry. Clone that repo if you're following along. Okay. Cool. No, fine. Whatever. Yeah. Yeah. So there's a Docker file in there. It should start up fairly simply. You're doing this on the Podman?
I'm using Docker.
Okay. So you may have a problem about The unspecified sources.
All Docker that? Point is to get a Postgres running. I have a Postgres running.
Okay. Do you have PostGIS on it? Yeah, well then,
Okay.
maybe what they need to do is get PostGIS running on your Postgres. That might be an easier exercise. I don't know.
Keep going.
All right, fine. Let's just keep rolling it. Okay, so for those joined a bit late, the material I'm using is from an open source training set that was built by the Postgres community. There's 6 hours of material there. We're going to pick sort of 2.5, 3 hours out of it for people who already have some clue about databases. So we're not going to do the very basics, but we are going to do some of the command line stuff relevant to Postgres for people who are migrating, etc., and then some of the performance stuff. So, all good. Right. Okay, we don't care. All right, so I think that's, if we are leaving these environment setups alone for the moment, we will then move away from that session and we will move on to the DBA basics. Okay, so we're not going to spend too much time on this. Some of the logical replication and connection pooling stuff could be quite interesting, but other than that, probably move through this one quite fast. So I think we all understand what your options are about where to run it. Yeah, you can use the various bits of Pacona software anywhere on the left and get services from us or anything on the right. Managed versus self-managed. Yeah, I mean, this is your trade-off, right? How much control do you want? We'll leave that. Okay, so backups. There are some bits that people leave out of Postgres backups a little too often, which is the configuration. Yeah, end up with a bunch of database files, a bunch of WAL, but not the bits that are necessary for doing the restores. The process of archiving the write-ahead log is built into the server. There's just specify a command and off it goes to copy them away. So that's how you get your point-in-time recoveries. All of this is also managed by any of the backup tools that you can pick in the market. Our preferred one is PG Backrest, which, if you saw my thing yesterday, is now back and fully supported and properly maintained, and all of that good stuff again after a little bit of a problem. Dumps. Yeah, this is a thing everyone goes through. There are times when dump and restore is really your option for certain complicated upgrades, or if you've broken something badly enough. But it's not a real backup. It doesn't have that clean snapshot nature to it. And also on big databases, it takes forever. One of my early Postgres consulting jobs, I was working with a crowd who'd taken an application that had been built against DBase, and they decided they needed a proper database engine, so move it onto Postgres. But the thing was built very much for every application, every client then having their own DBase file. So they just replicated these things across schemas. So 2,500 schemas, 30-odd objects in each. That is when logical backups really start to hurt, because the per object thing just gets out of hand. Physical backups, still quite a small database, but the logic's really gonna hurt you at that point. There is some parallelism available in pgdump if you absolutely have to, but yeah, not a proper backup. You can dump all. Again, one of the things about Postgres and where the objects live, which may catch people by surprise coming from other engines, is that the roles belong to the entire cluster. A lot of your restores, if you have particular permissions in them, aren't going to work unless you've dumped all of that. If you're doing a logical backup, restoring things with particular permissions isn't going to work unless you've dumped all the roles out and you've restored all the roles first before you try to bring all your tables back in a logical restore. Cool. Physical backups, as I was saying, great stuff. From a performance point of view, this is also the basis of any of the physical replication stuff. You need a starting point to start your replicas from. Point in time recoveries are an important thing for any kind of corruption exercises, any kind of people doing something silly, particularly developer environments. People may just go in and trash their dev system, and their restore, wind forward. This assumes you have all the WAL files. If it's just for your own development environment, you just set the retention period on the WAL quite high. If it's for big production systems, you need to make sure that you're moving those archives off, and that's a configuration in the configure on what command to call when a particular write-ahead log is full. Once you have a complete segment, move it off. Base backup will give you all sorts of options for how to do this. Obviously, when you're automating this for big routine operations, you're not going to see a whole lot of these options. You will want to put them in a tar. You will want to probably stream the WAL. So,
we're using Postgres 12, and we've been super frustrated with PG-based backup. All never get it to work.
So that was fixed in 15 or 16. There's the issue before that, and one of my colleagues at VMware put in the patch for this back in, I don't know, 2021 or something. The error handling on the WAL streaming, this -X option, only gets checked. There's a plug in front there, isn't it? Oh, it's a bit short. Okay. Yeah. The error handling was only getting checked once the bulk of the copy was finished. So if your WAL streaming breaks for some reason, and this particular bank had a very aggressive WAL archiving policy, so you did end up with WAL streaming breaking occasionally. It's not that it only broke at the end of the base backup, but the error was only reported at the end of the base backup. So you get all the way through copying your however many gigs, and then it's like, broken. So yes, that problem's going to go away when you make your upgrade to 17 or 18 or whatever, because the error reporting around the excess stuff is fixed. I don't know. Yeah. All right. We're gonna. Sorry. No, no. So the physical backup, it copies the underlying files, and it copies the changes while that's happening. And then the last phase of the restore is that you then roll forward to a consistent point by applying your point in time recovery to the point at which your backup finished. No, there's no lock. The consistency is achieved during restore, not during the backup. All right, so we've been talking about WAL a bit when we were sort of talking about what gets backed up. So WAL is Postgres's durability mechanism. It looks a little different from the redo log model that you'd see in the Oracle world, for instance, because it is a forward-looking rather than a backward-looking set of records. This is the first place the data is written. This is how your crash recoveries work. So if the server goes down, what is in memory gets lost. The underlying data files may not have been updated yet. So when the server comes up, you apply all the changes that were written ahead, and then you get your database back into a consistent state. It's fast because it's sequential. The sequence numbers in the WAL are a key piece of how we monitor a lot of what happens for things like replication. So there's the number of bytes down the write-ahead log that we have traveled, and this is the one log that's used for all the functions in the Postgres world. It's not like there is one thing that's replicated and one thing that's used for crash recovery. The bin log, redo log kind of separation that you see on MySQL. This is the one that matters. Comes with some of its own concerns, but yes, there's only one thing you need to look after. And the data gets into this during the client process from the in-memory copies of database pages. So any page which has been recently used is kept in the shared buffers. We'll talk a little later about how to size those correctly. It's not necessarily more is better, because there's certain housekeeping functions that can take a while to go reading through all of those pages. Once you've updated the copy of the data in memory, a portion of that page is then written out into the WAL. So the first time any page has been updated after the server startup or after the WAL has been synchronized, the whole page will write. So we don't end up with torn writes at a file system level. And then there are two processes that run through the background and make sure that the underlying table files are updated with the data from the write-ahead log. So the one that sort of stops the world to make this happen is the checkpointer. That is the process that makes sure that whatever is in your table's data files is the same as what's in the WAL. It's the same process that executes when you start a machine after a crash. So it's that crash recovery type of process. Potentially quite I/O intensive. There's a lot of discussion about quite where to set those values, which we'll get into in one of the later slides. And then there's a background process which tries to clean up dirty pages to make the next checkpoint smaller. So the completion time for a checkpoint is something you can configure. There can potentially be partial checkpoints if you want to keep the impact down, because you can, if you're not getting the settings around that right, you can absolutely saturate the IO at checkpoint time. And while you're then not logically blocking any database processes, you can just swamp the infrastructure and stop the world by checkpointing a bit too aggressively. Yeah, have you got you have a basic Postgres? Okay, so you should still be able to run some of this. Yeah. So there are various functions that you can see for the current status of your write-ahead log. So those two numbers you see there, the sequence numbers, they're expressed as a number of bytes into a timeline. The timeline is the thing that changes whenever we do failovers. So if a machine is promoted or demoted, the thing before that slash will increment it. And then the bit after that is it's really just a hex encoded byte count. Right, so I think we've spoken about most of this around sort of what WAL does. Your question about the locking and the rest of it, I think, is covered in that blue point there. The thing which gets us to a consistent position is that we've rolled the WAL forward, not that we've aggressively locked the file system during backup.
So rather than doing the MySQL thing, add a transaction. Copy everything and collect all the WALs during it.
Yeah, roll forward to a consistent point rather than store at a consistent point. Different philosophy. So again, depends on the databases, how you manage these things. Also what your requirements are for retention. There are people who still want to be able to restore systems to a point in time 4 years later for compliance reasons. So their EMC sales guy loves them because they're just using more and more and more storage. So this is just the summary around the physical backup. Base backup is the built-in thing. It's used by some of the backup tools, or some of the others have something that looks a lot like it. PG Backrest has something that looks a lot like it. It doesn't actually use base backup itself. There are manifests which will tell you whether the things are corrupted or not. The WALs can get archived. As I said, there's an archive command in the config, and that is one of the places where you end up connecting your Postgres system up to your corporate backup, so that so if you're working with a network or a Commvault or something like that, the archive command in the config file is somewhere where you're going to reference pieces of that backup tool to make sure that all the WAL is available on your backup devices for point-in-time recovery. There is an incremental backup option available from Postgres 18 onwards, incremental physical backups. And that then comes together with some tools for putting those increments on top of previous physical backups. So you can combine an incremental and a full, and then verify, because you have all the checksums and all of that good stuff. Incremental saves you quite a lot of write out to the remote environment. In order to ensure integrity, you're not actually saving that much read when you do it's network transfer and writes on the target environment that you're really saving. Backup tools, there are a range of other ones. What we package at Bacona is PG Backrest. We believe that's the thing that best matches everyone's requirements for enterprise backup. One of the things that's different about Backrest is that its protocol for managing the consistency between the backup target and the source server is something they built themselves for the particular requirement. Barman uses the rsync protocols for that, which comes with certain potential race conditions. WALG also have built their own. WALG is the successor to the an older thing called Wall-E, which was obviously created, named after the cute little Disney robot. Okay, now this one's fun. Where are all the versions? So Postgres has, for the past 12 years, done one major release every year, and there are 4 scheduled minors. It is like the Ubuntu release cycle, a what's ready at the time gets on the bus process. What that looks like from a code build-out point of view is that whatever is in the code base late April is what will then be polished up for release in September or October. So the window for adding new features to Postgres 19 was open from roughly April 25 through April 26. And we are now in the period of issuing the betas, cleaning it all up. This is the point where potentially, I can't think of anything that's going to get pulled out of 19, but this is the point in the process where there are some features which may just not be possible to polish, and they will get pulled out before beta 2. So now, there's nothing I can think of like that in 19, but we have seen a few features in 17 pulled out at the first public beta. There are also every now and again out of cycle releases. They're often around security issues, or they are around fixing issues which were created by security fixes. There's been sort of one of those a year for the past 2 or 3 years. The security team's a bit smaller. They are often reviewing code under quite a lot of time pressure, and unfortunately it does show that the review of those patches is nowhere near as thorough as the review of the stuff that ends up in the main tree. Postgres 14, if you're on it, you need to start thinking about getting off, because there are only 5 in support at a time, so 14 is going to disappear at the end of this year. Yeah, November 26 is going to be the last patch for 14, so start thinking about upgrades if you haven't already. Yeah, so minor versions, Postgres is very assertive about not breaking things in minor versions. The only stuff that's going to break there is things which were wrong in a way that affected security. So it's not never, but it's very, very seldom. Your minor upgrades should just be done routinely. Maybe wait a week after they're released, in case it was one of those things that had an oopsie in a security patch. But yeah, you shouldn't be getting behind. Major upgrades, our friends PG dump and PG restore come in. There is a tool called PG upgrade, which keeps your data files and rewrites the catalog. It comes with certain caveats, a lot of them around some of the big extensions, or you can logically replicate from the previous version. And that comes with some of its own constraints, which we're going to look at next. Has anyone here upgraded a Postgres in production with PG upgrade? Okay. Yeah, so basically the PG upgrade process is you need 2 copies of the binaries, old one and the new one. You potentially take a copy of all the data, so you have the option of completely replicating the data set, or you have the option of just sort of doing it by reference. By reference is going to be a lot faster, but you have no way of going back without doing a physical restore. But I mean, at certain sizes, it's the only practical option. When I used to work on data warehousing systems, that was the only thing we were going to do. We weren't actually going to wait to restore 400 terabytes. So, yeah, I think we will understand this thing. Extension compatibility is one of the tricky ones here. Making sure that your extensions work with the new version. Yeah, a lot of people don't really have robust test suites for that. The two times database size thing is a requirement if you are taking a second copy of the data. That can get scary if you have a particularly big database, and your rollback plan, well, if you've got twice the data, twice the space, rollback's fairly simple. If you haven't, that's a full binary restore, which comes with its own set of issues. All right, any further questions there? Nope. All right.
Not for use with cloud services.
You have to have full, yes,
Okay.
true, yes, that is, you have to have full control. You have to have a operating system user that owns the Postgres process. You have to have access to that thing. Your cloud providers will do some of this in the background for you, depending on how happy you are with all of that, yes. So just if we look at the sort of broad DRNHA stuff, I think we probably all understand these terms. Yeah. At what point can we get our data back? How long is it going to take us to bring the system up? High availability systems, things that we can automate are ideally things that don't lose data at all. So you have the computer make a decision about, okay, we can turn this one on if you're not making any decisions about losing data. If you are making decisions about losing data, it's really nice to have a person do that. So the basic model for the HA and the DR systems, Postgres, is moving these walls around. Synchronous comes in a few flavors. This is where you can avoid losing data, but it really does bump up your latency. There are a set of options for how to deal with that synchronous commit. So the default is that the WAL file has to have been transmitted and written to disk on the remote system. So you have an fsync happening on both environments, but you know that if both the servers crash, you still have a copy of it. The slightly cheaper option is just the remote machine is acknowledged, so it's no longer all on the primary. There's a copy of it somewhere else. It may still be in memory, you don't know. A little bit quicker, places less requirement on the storage issues. The really extreme version, which is only really used in multi-reader scale-out application environments, is that it has to have been applied on the remote side. So synchronous commit remote apply, the write-ahead has been transmitted, it has been fsynced, but it has also been checkpointed effectively on the remote side. So then, at the point where your write returns on the primary, you can read the replica and you'll get the same answer. But that does mean your latencies go through the roof. And it also means you're thrashing the IO on your replica. You really need a replica at least as beefy as your primary to make any of that work. You need it for synchronous replication most of the time anyway, but yeah. A lot of people do async because it is just so much faster. Not overall speed-wise, but latency-wise. You're not waiting. You can also change this at a transaction level. So if there are certain things you want to be particularly careful about. For your session, you can push the level up and then bring it back down to the defaults afterwards for certain particular admin tasks. These are the basic settings that we need in order to be able to manage this. So WAL level has to do with how much the server tries to optimize the amount of data written to disk. So if this is left at the default, you'll see a little bit of reference data, the record you updated, and a little bit of reference data, and that's it in the wall. Replica, you have a bit more context each side of the row. There is also a higher level, which is used for logical replication. That gets very big because you're writing old and new versions of the rows for the logical replication system to be able to dig up. There are a few settings around managing how much disk space wall can take up, and this fights with various other aspects of replication. The amount of wall to keep it down, but it does mean that you will then not be able to synchronize a replica if it's been offline for a while, if you don't have the wall available on the primary. You may need to go and fetch it from the archive. That makes the setup of your replicas a little more complicated because they need to know not just about your primary, but also about whatever your backup system is that you're now copying all the archives off to. It's an issue of more complex configuration. What happens in this process? You promote your standby, having first made sure that the primary is no longer writable, and there are a whole lot of ways of dealing with that. And then you need to make sure that the application is connecting to the right primary. That's what I did a talk on yesterday. There are various automatic things for managing this. Patroni is the one that we ship as part of Bacona's packaging. It deals with issues like maintaining the list of synchronous standbys. So if you have 5 servers and you now move the primary, it'll take that new primary out of the list and add in the one that's just been demoted and manage all of those sort of settings for you. Rep Manager is another alternative, but most of the attention these days for the client-side tooling that isn't managed by the cloud providers is going on Patroni. There are a few other solutions that have been essentially retired in order to make that work. PG Auto Failover was one of them. That was something that Microsoft had built for Citus and got killed off when they hired the Patroni guys to make Patroni play nicely with that stuff. Again, if you're working in a hosted environment, that's all going to be different, particularly if it's not a Postgres all the way down to the storage layer, like Aurora or Alloy. All of that changes because it becomes tied with the storage layer. Yeah, so quick look at the Patroni config. There are cluster names. Sort of what group am I a member of? Cluster, unfortunately, is one of those overloaded terms in the Postgres world. A machine running multiple potential databases with a cluster of processes that are serving queries is something that the Postgres documentation talks about as a cluster. What we're talking about here is what's the collective noun for elephant's herd. But unfortunately, Patroni docs use the same word for a cluster of clusters. Patroni relies on an external provider for external provider for reconciliation and quorum, generally etcd. Console, I think, is another one that some people use. We're not going to do much sort of hands-on with that today. It's a very big thing to set up and test. One note on setting these things up: etcd is very, very sensitive to I/O disruption. So in environments where you have any kind of I/O constraints, try to avoid running the etcd and the Postgres on the same box, where you can get stuck in a very fun loop where when you try to create the replica, the copy of the data from the primary saturates the storage. etcd can't f-sync the heartbeat. Every time the primary issues a heartbeat, etcd writes a timestamp to disk. That's an f-sync immediately. So if that can't happen, leader is regarded as being dead, forces a leader election, your attempt to build your replica stalls. Yes. Or behind a different I/O quota. I mean, it all depends what your infrastructure looks like. The place where I saw this go worst was a bank where they'd managed the cost of the storage arrays by divvying the available IOPS up among the various VMs. So they were, although they were on some quite big infrastructure, they were fairly IO starved. And Postgres and etcd ended up fighting over those available IOs every time. So we've looked at physical replication. Logical replication is taking the contents of the row as your application would understand it and transferring that rather than transferring the physical representation on disk. This has some advantages, like it doesn't have to be the same version of Postgres. It also doesn't have to be everything on your server, because the process for moving the WAL is there's one WAL for all the databases on the machine. In the environments we see with sort of cloud native applications these days, that doesn't matter, because there's often just one database on a machine. In older configs, there's still just that one file, so you're replicating everything. So that's the upside on logical. The downside is that you need to decode all of the stuff. The logical replication is not built as an event on the server. It is something that processes the WALs to then produce the replication. One of the reasons that we see people reaching for logical replication when they're using binary, when they're using the physical for everything else, is to manage downtime during upgrades, to make sure that the two systems of the two versions are in sync before the failover happens. Obviously, then there's also the consolidation case. You know, there's a lot of CDC tooling built on top of the logical replication framework, which can get you all of your, update all the 10 or 12 transactional systems into one central environment, all of that sort of stuff. Also, architecture differences, I don't know. I'm not sure I'd want to run an environment like that anyway. One big Indian box, one little Indian box. It doesn't sound like a fun place to be. All right.
So one of the things that I learned Postgres in '96, so I have a lot of that in my head. But one of the things that I was told by there is that logical replication is dangerous because replica stops. The walls build up on the master.
So there are 15 or 16. There are safeguards against that. So there are. So there's the max wall size we looked at earlier. That does not include things that can't be destroyed because they're still part of a replication slot. There is a setting, I think it comes in at 16, for the maximum amount of wall per replication slot. So you will see an error and the replication will be evicted effectively. No, this is no longer a replica because there's too much data stacked up behind that. Yes. It means that recovering a replica is going to be a huge pain in the arse. But rather than take the whole system down, that's the trade-off you get to make if you set that. It is not set by default. So the default behavior remains as it was historically, that you can just pile the stuff up until it all goes bang. Since we don't seem to have anyone following along, we'll skip the hands-on. Just briefly, create publication is the server side. You can create a subscription. The publish, subscribe, nice and easy. Watch it replicate, all good. Like everything, there's a whole lot of stats on it. So PG replication slots is the thing that is the system view that gives you all the information about what's going on the replication side. On the subscriber, you can look at stat subscription, so you can get a feeling for how much you've received. Okay, clean them up. Okay, now another thing that the replication stuff places some pressure on is connections. Connections to Postgres are fairly expensive. If you set the defaults fairly big, you end up allocating a chunk of memory. They are pre-forked processes, etc. And there's a table stat activity which will show you what's happening on each connection at the moment. This gets a little more complicated now that we have parallelized queries. You'll see multiple bits of parallel queries when there are additional backends. Max connections is the thing you use to protect your server from running out of memory from too many connections, and you can then have a few more of those to connect to super users. We've spoken about this, about the overhead. Connections get stuck in idle. It may be an indication that somewhere in your application estate you need to do something, and that something may be a connection pooler. On the other side, though, if you have a connection pooler that maintains quite a big block of open connections, obviously you're going to see them idle because the connection pooler is going to open them the instant it starts up. So just be aware of what's sitting between you and the application if you do see a fairly constant number of connections. So we were having this conversation over a beer last night. PG Bouncer is the most popular of the connection poolers because it's simple. It's not trying to do very much. Just open up a set of connections, take requests, push them down one of the open connections. That's really what's going on there. It was built originally for the problem of simple applications thrashing the target database by opening and closing connections often. That's a fairly easy problem to manage. When you start looking at some more complex situations where you get a lot of things stuck inside a session, so you change some of the parameters for a session. We were talking earlier about maybe changing the durability requirement for a particular session, changing the synchronous commit requirement on a session. That starts to get a lot more difficult to manage. If you use prepared statements, the way Postgres manages those is they are attached to a particular session. So it gets more difficult to reuse connections if you have a bunch of that stuff going on. Pool modes. The session mode is the thing that I was saying is great for preventing thrashing. Transaction is the most common. Statement is the mode that was used for the thrashing. Transaction is the most common. Once a transaction is open, you need to stay on the same connection until the transaction finishes. So there's something that carries with you, but not all the other stuff like your prepared statements, etc. And then your session is if you're doing all of these things, all of these complicated things at the session level, and then no one else can reuse it. It's a lot less useful. You're really just using PG Bouncer to take the overhead of the reconnection off you.
Bouncer just last year finally got allowed.
Yes.
So now that's only in session.
Yeah. Yes. Yeah. So I mean, there's a lot of talk about how to pull everything that exists in a particular session out and be able to transfer it around. But I mean, that is so deeply wound into so many places. But yeah. PG Bouncer like a lot of these connection poolers, exposes its config, exposes its data through a virtual database. You can go in and you can run various set returning functions, and it will tell you, what's going on. So, show me the pools. Okay, so any example we have, and there are a few other things you can see about what's going on at the time. So yes, very simple answer for most common of the use cases, but there are some more complex things out there. pgdog is one that's dedicated to Postgres. It's also, they're doing some work around sharding at the proxy layer. So the proxy has a view of tables that have different data ranges on different machines. A little more commonly, pgdog and pgpool2 and proxy SQL do read-write routing, but that then requires that you are parsing statements on the proxy. Okay. Postgres MVCC, I think everyone's probably aware of this. This is the number one stick everyone wants to beat Postgres with. Why are there still dead records in your table? And there's a process to go through and mark them to be reused. It keeps the locking model quite simple. It keeps rollbacks quite cheap when you abandon transactions, but the stuff accumulates. For tables that you are thrashing particularly heavily, where you're going to be updating particular records a lot, there is an option for avoiding some of this if you are willing to waste some disk space up front, and that is reducing the fill factor on the table. So the process of Postgres updating a record is generally that the old one will be marked obsoleted and the new one will be marked active. But if the page that record is on is full, the new record's going to have to end up on a new page. And there's no easy way to then remove the old one in line during the query. If they are on the same page, there is the heap-only tuple, the hot update. That's what hot updates stand for if you see them in reference to Postgres. Where the old record, once its visibility threshold has passed, can then be reused implicitly because you're not invalidating anything else. You're not invalidating any of the indexes. The index still points to the right page, to the right logical slot number on that page, and then there's a redirect saying, actually, no, it's in this different slot on the page. So that can keep the amount of bloat generated when you're thrashing a record down, if it's a record that you can fit a reasonable number of into a page. You can avoid some of these bloat issues by allocating data less efficiently in the first place. So if you keep your fill factor at 50, half the page is empty. You've got some space to thrash around on your records. Vacuum, fine. The one at the bottom isn't actually a vacuum. Vacuum full is actually a repack of the table. In 19, it now has an alias. There's now a repack command, which is at least a little more honest about what it's doing. So the basic vacuum just goes through, and if the space can be reused, removes the marker at the top of it, and you can then go reuse it. The table will stay the same size it currently is, even if the middle 90% of it is all empty. Full actually rewrites the whole thing. So you copy only the currently active records, but it is an exclusive lock. You can't have anything else going on at the time. So it is a bit of a stop the world option. Something that's often done while you're vacuuming, because you're in the table, you're reading everything, is to update the planar statistics. So that's what the analyze option is about. There is also something that runs around in the background and cleans up after you if you let it. This is one of those places where the default settings are probably wrong for a lot of people.
everybody.
No, you can't. But I mean, a lot of Postgres' defaults are built for things smaller than Raspberry Pis. The very small shared buffers and all the rest of that. But yeah. So yes, this is stuff you probably want to fiddle with a bit on production boxes. Having to have 20% of your table wasted before you go trying an auto vacuum seems a bit high for a big table. You probably want that more like 0.05 or something on biggish tables. You also have a question about how many of these workers to start. Fairly easy to check the bloat. There is an estimate of the number of active rows and inactive rows stored in one of the catalogs. That heuristic doesn't always work. Those numbers can be off, but they're generally a good enough indication. pgstat user tables, pgstat system tables, pgstat all tables, those catalog views will give you some kind of idea. There are a number of extensions for playing with this. StatTuple is one of the things that's in Contrib, so you can just run the create extension on any default Postgres system. Your mileage on cloud providers may vary. Of course, the issue really the ugliest issue we can bump into it when we end up with bloat is that we can run out of disk space. There are functions for reporting the size of tables. Alrighty, are we supposed to be having a break? We're now an hour in, aren't we? Okay, I've got another half hour. Cool. Yeah, so I don't think we need to spend too much time on partitioning unless anyone has any particular questions. It's all fairly simple. You just stick the record in the right table. Ideally, you partition by things that end up in your query predicates so that the planner can figure out which tables to eliminate. There is dynamic partition elimination based on values, but obviously that will end up more conservative than if it's actually in your predicate, and it's very clear. The other big reason, of course, to do partitioning is if you have data lifecycle processes that involve destroying data. Doing a big delete under this MVCC model thrashes the disk hard, you end up having to clean up, etc., etc. If you have a well-known pattern for destroying data, you just roll the partition off the end and destroy the partition. That can save you a lot of trouble. The parallelism of partitions works okay for scans. There is a set of planner options to allow you to, if you have two partition tables and they are partitioned in the same way, manage things like joins between only the partitions that match. It is turned off by default because it means that the planning complexity explodes. So it's worth experimenting with if you have problems like that. Yeah, if you have event tables from two different event sources and you sort of want to correlate them, that sort of thing, where you could have the same partitioning scheme on both tables, but do experiment with it before just turning it on, because you can end up with some horrific query planning times as a result. Yeah, I think we get this range is the most common. Hash distributions, really, if you just want a certain number of partitions to do things like simplifying your vacuum processes, etc. Certain query, fine. Yeah. Turning a non-partition table into a partition table is very intrusive. It's a complete rewrite. You're going to have to stop the world. So doing it early is nice. There are also obviously certain constraints around partitioning and unique keys, because any index only operates within a particular partition. Our partition is a first-class table in any other way until you're trying to query it. So if you have any kind of unique constraints, you need to have those in your partition key as well. Right, so we've got through that one. Any questions at that point? Anyone still awake out there? Cool. All right. So, yes, so there's a little less hands-on in this one, but we don't seem to be doing a whole lot of hands-on anyway. All right, so if we're going to go looking for information about our system as it's running currently, where we go is the catalog, all the stuff which the database can tell us about itself. When Postgres systems are initialized, there's a certain set of catalog tables that are set up. Everything about the data, everything about the database is in real tables, and they behave like any other table. You can, if you have a lot of thrashing in your application, destroying and creating objects, you can bloat your catalog tables in the same way you can bloat any other table. They really are real tables. There's then a set of statistics views which run off the in-memory cumulative statistics models to give you information about what's happening right now. So for instance, we looked at the pgstat subscriber and pgstat replication slots once very briefly in the section on logical replication. Those are things that are managed by the cumulative statistics system. So, the very basics. Some of these things have slightly funny names due to the academic nature of where Postgres started. These are sort of they're named according to how these ideas are referred to in the academic literature around databases. Database, nice and easy. Next one down is PG namespace. That's your schemas. PG class is all of your relation objects, tables, indexes, all of those things. Attribute is your columns. So index is the additional information on top of what's in PG class that you need about an index. So for instance, in class, you'd see that the index exists. You'd see what fields there are in it in attribute, but in PG index, you'd see the link back to the table that it's built on. You'd see any information about which of those attributes in the index were things that were actually indexed and which were additional covering index information. PG proc is all your functions. Quite a big table, but that's an interesting place to have a look at, for instance, what the overloaded functions are, because it also contains the function signatures for the parameter types. Users and roles. So PG class is a fairly simple table. It contains some intermittently updated estimates around the population of the table. So this is where you'll see estimates around the number of records. Things like live tuples and dead tuples are kept in a pgstat thing because they're updated a bit more often, and they're only written out to disk on graceful shutdown. So we have the kind. Regular tables are user tables. There's S for the system tables, indexes. This is the most important of the system statistics views, pgstat activity. What's going on? Because this is a pre-fork, the identifier here is the process ID, and that is your operating system process ID that's running the query backend for this particular activity. We can see a few things about how the connection happened. who is the user? Where do we think they come from? Obviously, if you've got poolers in the way, that's going to be the pooler. Applications can also report an application name when they connect. In a replication setup, what you see is the application name will, by default, be the server name of the replica. You can see a few things about whether there's a running query, when it started, how long ago it started. There is a very big piece of query text. You probably wouldn't want to use that in full on an interactive screen. So we also had a brief look at pgstat user tables earlier around bloat, system view around live tuples, dead tuples, and also some things around auto vacuum activity, analyze activity, which you'll see in that catalog. If you are having some troubles with auto vacuum, that you believe it's not looking at the right tables, this is where you'd find evidence of where those auto vacuums had happened or hadn't happened on any of your tables. If you have partitioned tables, you're going to see every partition individually in this, because they are saying, other than for sort of the query routing point of view, they are full-blown tables. Indexes, fairly well understood. This is where you would spot indexes that weren't being used. So these counters are updated when queries are run. If you have indexes that are just never being used, you're going to see some very different numbers between here and the pgstat user tables, because one of the other fields that you can find in here is the number of times the table's been scanned. So that mismatch would give you okay, this index is never being used sign, and obviously those are not completely free, because you do have to pay to update them. Locks, I mean, we can go down some very deep holes here, but very basically, what's locking in what mode? There is a granted column for, have I got the lock? If that's false, we can start looking through self-joins on the system view at what's getting in what's way. A lot of the monitoring tools that sort of give you a query weighting analysis, it starts from PG locks. This is the range of them. At the bottom, access exclusive. This is what the really big intrusive operations like a repack require. And then all the way down to access share, which is basically, I'm reading this at the moment, just putting up a flag, so that the more intrusive locks can't then go and grab the object. So this is a bit of an eye chart of a query, but this is the what's getting in what in whose way query for looking through the locks. So we can see that we're looking at pgstat activity, PG locks to build a picture, and then joining that up with that array-ag function is just something which, in the order it finds them in, will build you a list. So what we're going to get at the end of this is a list of the PIDs which are queued behind a particular process that's holding a lock. Logging is good, right? Yes, fantastic. Moving on. Yeah, so the logging settings are fairly complicated. Logging collector is a process which takes the output of the backends and manages writing them somewhere. So if we're running them in a container, that's off. Things just keep spewing out a standard out. Most standalone systems on VMs have the logging collector on, because the logging collector is then what manages redirecting your log output to syslog or to a rolled over log file or whatever. Yeah. So once you've got your log collector on, then there's the question of, okay, where's it logging to? Log statement is a very coarse thing of what categories of statement do we log. So are we logging DDL? That's something that we see on quite a lot of systems where the statement about anyone changing structures, everything gets logged. And then the queries, we pick which ones to log, either because they're too slow, so the min duration, don't log anything that took less than however many seconds. So here's just the example. Got the log collector on, and then set up all the file-based logging. This is something that is managed by the postmaster process, the Postgres daemon process, so it only takes effect at restart. Okay, look at our logs.
Running the syslog, our syslog or something. File.
And where were you managing to run into trouble with that? Did you run out of disk space and flatten the whole thing? Yeah. I mean,
if it's writing every single line, and we have it right into everything that takes over, I don't know, thought we were being smart.
Yeah, well, firstly, you run a very real risk of running out of disk space. But yes.
I captured that. The IO is what I didn't capture.
Yeah. Severity levels, this is the other thing, yeah. So by default, everything from warning upwards is logged. Depending on your environment, there may be certain things that you are doing perfectly validly that generate warnings. So it's fairly common to see min bumped up to error. Statements, none, DDL only, anything that modifies, so DDL and updates and inserts, or potentially everything. I mean, that's obviously quite a challenge.
Datadog or system will give you, might not give you the same aggregate view, or nice to have two different points of view. A lot. Badger wants a verbose log. We made it very verbose.
Mm-hmm. Yeah, so yeah, it's to do analytics on. I mean, most of the systems that you'll see in the wild with the logging turned all the way up are development systems, so that the developers can see what's going on. That logging does not provide particularly useful auditing because you don't see what's hidden behind views, you don't see what's hidden behind function calls. There is an extension called PG Audit, which hooks into the permissions infrastructure. So it will tell you exactly what is being accessed by every statement. But if you really want verbose logging, that's where you go, because every statement is going to generate information about which tables got accessed, which fields got accessed, who was the user, were they accessing it as themselves, or were they accessing it using sort of the permissions of the view creator? All of that information, great for security, great for instance, finding privileges that aren't being used. That's a sort of classic audit thing. Okay, we've got a month's worth of data. What privileges do we know we've allocated to users that aren't in use? But it is very verbose. So DDL, anything you change the schema. This is something we see quite commonly used. You want to know when somebody did something that potentially breaks the data structures. And then the timing for how many queries do we want to log? What are we talking about being slow? Unfortunately, this isn't something that can be set at session level. That would be lovely. Yeah, this particular session should be doing certain things. The infrastructure is a little further up than that. This is server-wide, and you need to reload the cont for everything. So yeah, the min duration statement is what gives us that. Also, anything that broke, any statements that didn't execute successfully. This is on by default. So if you have applications that are doing silly things, generating bad queries, you will see every single one of them. So are you expecting tables that don't exist, etc.? You can put a whole bunch of information on the front, usernames, database names, application names, basically everything you see in pgstat statement. You can also stick on the front of the log line if you want. You can also log anything that gets killed by deadlock. Very useful as well if you have misbehaving queries. Simulate that. I mentioned PG audit. Does all sorts of additional bits and pieces. Yeah, we could spend a lot of time on that, but we'll give it a moment. Yeah, so all the bits and pieces of the statement. All right, onto the meatier bit of this. We're supposed to break in 8 minutes, aren't we? Right, so I think before we start that, let's take our break a little early, and we'll, rather than cutting this section in half. Yeah. I will see everyone back here when are we supposed to restart. Cool. So we're going to talk about some of the common problems we have on troubleshooting. I think we understand most of these quite well. They're quite common to most databases. You know, you have queries getting in each other's way. You have locks that just won't go, etc. So long-running queries. We go back to our friend pgstat activity, which maintains a timestamp of when a query started. So if the connection is not idle, and you can then assume that start time is the duration of the query. So find the long-running stuff. Reasonably simple. Idling transaction. So this is one of the big problems with some interactive applications that have been built a little badly, where I have seen applications in the wild that wait on user interaction in the middle of a transaction, and you can really end up tripping everything up, because while you're idling in transaction, you could be holding locks, and then all sorts of things can queue up. And then we go back to this query around the blocked query. What PID is waiting on which lock, and this hopefully won't, but realistically often enough ends up correlating with those idling transactions, that there are locks they have that things are queuing behind. So there is a way of cancelling a query. You need to be a super user for this. So on your favorite RDS, you don't get to do it. Cancel backend.
How do you manage RDS?
I don't know.
Oh,
I don't know.
Interesting.
Sorry, no. You can get that one. You can't get this one. The terminate. Okay, you're not listening to me. Hit it on the head. This may leave a little bit of mess behind. Right. There is also a way of sort of making this happen automatically. So you can set statement timeouts. This is probably good policy anyway. just as a default behavior at the application layer. What the right value is depends on the workload. So it's probably not something that I'd suggest doing with a sort of an alter database, for instance, to say, we won't let queries run longer than X on this database at all. For users, if say you have users for your data loading app and you have users for your reporting app, you can probably set up something a bit different for them. I mean, this really protects you against having queries that get stuck behind locks and then the application just never finds out. The whole thing falls into a hole. At least if you have a statement timeout, the application is going to get some kind of error. You're going to be able to keep things moving on the application user end. There is also new in 18, I believe, an idling transaction timeout. Use with great care, because it means you're going to be rolling something back. You need to have a pretty good idea of what it is, or be very sure that the developers are doing something trivial before you do this, because it is unlikely you're going to be idling transaction and have no updates pending in that transaction. So there's a great likelihood you're going to roll something back. It doesn't disconnect the connection. It just kills off kills the transaction and reports back a failure. Yeah. Don't wait forever for locks. So this is an alternative to setting generic statement timeouts. If you're particularly concerned about things getting stuck behind locks, you'll get your timeouts with your statement timeout, no matter what the cause is. But if you particularly want to deal with only locks and let everything else run as it wants to, you can set a lock timeout. And you will get back that error if something goes wrong, because you can't acquire a lock. So far, so obvious. You want to monitor things so that you get it right before users notice. This is capacity planning. It is baselines. There's all of those good things. Obviously, we want some infrastructure monitoring. At the Postgres level, this is all stuff you need to baseline, because this is going to look very different for every application. How many connections do you have open? Baselining that will give you a reasonable denominator for figuring out how much, for instance, work mem you can allocate for processes. What does a good transaction rate look like? Yeah, if it starts dropping, it's all obvious enough. Cache hit ratios as well, very dependent. Yeah, benchmark them. They may even move during the day, depending on what your systems do. The two that really just need to be as low as possible is replication lag and locks. Yeah, zero is better. So our connection count. Yeah, track the database growth. Some of this is stuff you're going to have to keep histories of somewhere. So tools like Postgres Workload Analyzer, Power. For those of you from the Oracle world, it looks quite a lot like the Oracle Workload Analyzer. That's what it was modeled on. But it takes snapshots of a whole lot of the stuff over time and puts you in a position to then answer questions like, why was something slow at 2 o'clock yesterday morning? Because you'll have a picture of what some of these things looked like at 2 o'clock yesterday morning, because really all of these PG stat whatevers are since they were last reset. You don't know how quickly they were arriving. Right? Cache hit ratio. This is in every entry in PG database. There is a bunch of I/O information about the number of blocks that have been read, the number of blocks that have been read from buffers, etc., etc. So if you look at the number of hits, so the number of cache hits divided by the total, you'll get yourself a number. Again, depends on your workload. You know, the more analytical type, or I mean, it may even not be, it may be sort of producing personalized navigation for individual users, those sorts of things. You may end up blowing out of your cache because you can't actually keep that for every user. It just depends on how lucky you get, whether they're all sitting in the same page. There are a number of open source exporters for shipping stuff to Prometheus for Postgres. pgstat-monitor is actually something that is mainly maintained by Bacona folks. It's an extension to PG. It's a pgstat statements plus, which brings in various other information. It's got a similar structure, plus then a whole bunch of stuff on the end. pgwatch is from the guys at Cybertech. Interesting sort of online monitoring tool. And then yes, on the offline side, you've got Power for that sort of long-term workload analysis. You've got various log analyzers. Probably the top one of those is Badger. Various ways of looking at that stuff. And if you want to spend money, there are people you can spend money with. Some of the usual suspects who are trying to apply their solutions to everything. pganalyze is one that is very specific to Postgres. They've done some interesting work around parsing and analyzing the queries themselves. Fun piece of sort of C programming geekery there, where they pulled the parser section of the Postgres source code out, and they actually use the real Postgres parser for parsing. Yeah, I think the project is actually called PG-Parse. It's an interesting thing as a how do we make sure these things are happening in the same way kind of project. So you'll see template queries like this all over the place around, you know, the things that you need to look at. You know, just what's active, what's stuck, what's our oldest transaction? That could be interesting. You know, how long are things hanging around? Where can you get some more information? Well, firstly, if you're a Bacona customer from us. Otherwise, you know, the community are generally quite helpful. I spend a fair amount of time on IRC. The docs are pretty complete, but we were having a discussion about this yesterday. There is a sort of an informal culture of inform but don't recommend. So people will sometimes look at the docs and find them looking a little thin because here's the information, you need to go do something with it. Is an informal kind of culture around writing some of the docs because of the question of how applicable some of this advice is to everybody. The Slack isn't really that active for something interactive, IRC, and mailing lists are still a big thing. PGSQL General is still a very active mailing list, and you will find committers popping up there answering people's questions every now and again. Oh, as a yes, as a source of sort of something to supplement the documentation, I suppose. Yes, we have all of our support techies writing what they learned in this week's support cases type blogs. So yeah, there's some interesting stuff there. Yes, that's all fine. Why didn't we make out to this? Anyway. Yeah, so that's our summary of the stuff we've gone through there. We've talked about the system catalogs, how we log stuff. Yeah, cancel, which is kind of nice-ish, and you can do it without CPUs that terminate, bit of a bad hammer. You have to have full access. All right, config and performance tuning next. Questions at that point? Alrighty. Go away. You go away. Oh dear, oh dear, oh dear. One of these diagrams. What we're looking at here really is in the bottom half of the picture. We had a slightly different version of this earlier on. Postgres being a pre-fork process, every backend has its own little process that will read from the shared buffers. It will write changes to the WAL. And then, because Postgres relies on the operating system's file system, there is a second layer of buffering for the operating system cache, which is why when we are setting the shared buffers number, we don't want to go over a quarter, even on a fairly small system, because you want to leave the operating system to do all of its own stuff. On big boxes, even going to a quarter can get you into some trouble, because cleaning up that cache, just those clock sweeps, can begin to take longer and longer. All right, I should have waited for that slide. Now it's a little more visible. Yeah, so IOPS, we've been talking about these a lot. Yeah, this is where you get all of that. The actual number of IOPS may not be an entire reflection of the number of operations your database is issuing, because the operating system may cache up, may bulk them up into fewer bigger operations. If you're looking at, say, your storage hardware stuff and your Linux stuff, you can see them mismatch. But that'll be something your operating system team and your storage team should know about. Now, besides the user backends, there are a whole bunch of other processes that run. You know, if you do a PS and you grep for Postgres, it's not just your query backends and your postmaster that you see. There's a whole bunch of other stuff. So we spoke earlier briefly about the background writer, which does that process of taking the dirty pages and updating the files on disk so that the checkpoint operation becomes smaller. The checkpointer process is the thing that periodically just smashes all of those changes out. Quite how to set up checkpointer is another point of debate a lot of the time, sort of how to get that period right. If in systems where you update the same record quite a few times, if the checkpoint period is too short, you'll end up writing that record to its target table again and again and again every time the checkpointer comes past. Rather than, if you set it a little bit longer, you'll have all of those updates will be through, and you'll only write it out once at the end of the process. The downside of that is that anything that hasn't been checkpointed is going to have to be recovered from WAL when the system starts back up. Now, that is not the same as the checkpoint delay. You're very unlikely to spend that much time replaying the WAL as you spend waiting for it to accumulate. Most of us are not, well, hopefully, not running systems where the restriction on performance is how quickly you can write WAL to disk. If you are, then yes, it's going to take you as long to recover as it took you to write the WAL, but that's very unusual. We spoke about log collectors. Extensions can create various background workers themselves. So you'll see some background workers of various kinds. One of them that is created by the async IO subsystem on Postgres 18, if you've turned it on, and if you use it in worker mode, is the IO worker. Probably anyone who's using Postgres 18 with async IO on Linux boxes is using the IOU ring features of the kernel. It's unlikely to see those on Linux boxes. You'll see them on BSD systems and the like for async IO. Right, we spoke about that briefly. Shared buffers, yeah, famously, this is one of those things that is set very, very low by default. So bump it up, yeah, call it 20, 25% of RAM, because you want the operating system, you want the working memory for the queries to still have something. On analytical systems, it's a lot less important. You're a lot less likely to be able to cache meaningfully because you're going to read into your database, but you want a lot more for working memory. Yeah, so beyond 32 gig, there are diminishing returns because you have to go clean up. I mean, people do run Postgres on 256 gig machines. It happens. How big are your shared buffers? Okay. Yeah. So you'll be paying a bit of processor overhead for keeping that clean, but yeah.
You got 96 cores.
All good. Yeah. 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 So effective cache size is not a setting around how to allocate memory. It's just a hint to the planner as to what it can assume reasonably assume is being cached. So that is your shared buffers and what you believe the operating system is using, which we'll assume is the same number. Don't know. We talked about cache hit ratios earlier, half an hour ago. So another interesting extension, buffer cache, will give you some information on what is being cached. So you can get a list of which blocks from which tables are being cached. Just a feeling for how much of your smaller tables are there, whether your bigger tables are repeatedly pushing that smaller stuff that you were hoping was just there for joining to out of the cache. That's an interesting sort of view to get. Again, one of those things that you want to take periodic snapshots of so you can have a look at it over time. Workmem, so this is what's used for processing queries. You sort, you join, etc. But it's not per query, it's per operation. So if you have multiple joins, multiple aggregates, you're going to end up using a multiple of workmem for your query. This is not divide the available memory by the number of backends unless you know you have very, very simple queries. This is also something that is set per backend. So if you have applications that have different behaviors and you want to tune it for each of them, you can do an alter user set, and then whenever the sessions appear, you'll have that set up in the correct way. Yeah, mainly I think as a way of reducing memory usage for those backends that really aren't going to benefit from it. So, there are indicators that you are running out of workmem. If you do an explain analyze, if you actually get all the output from the explain, there is an option there to show the buffers. Now, from 18, that is on by default. That buffer data is in the output by default. But yeah, if you're running multiple versions, just put buffers in there, and you will see different kinds of sort methods. You'll see different kinds of hash methods, and then the amount of what looks to Postgres like disk I/O that happens. You can't at that point tell whether it actually ended up on disk. Those operations, for instance, don't force F-syncs. Their durability doesn't matter. So it could all just end up in the operating system's caches. There are certain specialist categories of work memory. One of them is maintenance. So these are operations like creating indexes. So you can say that that sort of operation gets a lot more memory. There is then a subcategory of that, which is for vacuum. So there is a vacuum work mem as well. If you haven't specified that, the maintenance work mem is what will affect the memory available for vacuum. Yeah, we discussed this briefly. Yeah, so how often do we force a checkpoint? How much WAL are we willing to have outstanding before we force a checkpoint? So this essentially is how much we'd have to roll forward at max if we had to do a crash recovery. Because checkpoints are very I/O intensive, there are some options for making them less intensive. The checkpoint completion target, so how much of the available WAL do I want to be able to get rid of within that checkpoint timeout period, is how we can manage that process of just how hard we hit the I/O in the process of checkpointing, because that can, if you don't govern it, stop the world. Yes, there's less work for the checkpointer to do if the background writer has been keeping up. Yes, but yeah, it's all just about trying to keep this all as background noise rather than the one big hit sort of dropping the brick in the road. This is a topic of such debate. Postgres operates a cost-based query optimizer. And the unit of cost is the infrastructure cost of reading one sequential page in a file. That's the unit. So reading random pages is more expensive than reading sequential pages, even on SSDs, because all of them have got some read ahead and whatever stuff going on in them. So it's not one. Default value based on a whole bunch of tests on spinning Rust years ago is 4. There was a big debate in the Postgres 19 development cycle about changing the value. And some people who did some tests and they said, 1.4 was a good number. There were some people who did some tests on some of the enterprise SSDs and reckoned that actually the number should go up above 5 because of the built-in read-ahead behaviors. So it is a very contentious issue. Check it for your own infrastructure. Run the queries against the big tables. Tweak the number. Figure out what works best.
What's the effect if I have
You will use indexes more often if this number is higher. So the trade-off for the random thing is that you will use indexes less often if the random cost is higher. So the very simplistically, the comparison is between just running through the table or reading a necessary number of hops in the index and then a random page in the table. As you end up with the row assessment with estimated number of rows, approaching the number of rows in the table, this starts to matter a lot less, because at some point the assumption is that that you are going to be reading a material number of the table's pages. So that's very crudely how for a set of reads from a single table, it'll make the decision. So what proportion of the table is it reading? And then how is the cost of reading a few pages out of the index? Because the indexes also have information like the depth of the tree and that sort of thing. Those costs are added up. Estimated number of pages out of the index, estimated number of pages out of the heap. Yeah, bit of a foot gun as well. You can.
I mean, it's interesting because, like, reading the index is always better. Well, I think it was just 2 hops away at this.
Yeah, and not if it is too much of your table. Because then you're going to end up, because obviously covering indexes change this as well, because then you don't have to read the page out of the table at all. So covering indexes start to change some of this as well. The base assumption, if you don't have a covering index, is that you're going to have to read the page out of the table anyway. So you can add extra fields onto the end of a B-tree index so that you don't have to go to the table, index-only scans.
Okay.
You probably won't have met them yet because you haven't caught up with modern Postgres. But for some of for some of those heavily indexed reads, it can be very useful. So one of the things that has been a bit slower coming to Postgres than it has to some of the other database engines is parallel execution of queries using multiple, and it's not just multiple CPU cores, it's multiple processors, and therefore the limit of how much I/O a process can do, you get multiple of those behind you as well, because there is a question of how much I/O you can do with a process, and one process will not be able to absorb all the I/O capacity of the machine. So that's how it plays for sequential scans. For the hash joins and for the aggregations, it's obviously just a question of parallelized computing. You have multiple cores calculating hashes, multiple cores adding numbers up. There is some parallel index scanning in Postgres 17 that relies on certain assumptions about the shape of the tree. It's not always possible to parallelize. So there are a whole bunch of knobs to tweak here. How many parallel workers can you start in a single operation? How many can you start overall? And we again come to the cost. If we are doing this in parallel, what coordination overhead do we add to the cost estimate for having done that parallel scan, and at what size table do we believe it's worth it? If you have a big enough table, take roughly the middle of the block range, and one of them will scan each. We obviously have to then change some of the stuff in the back end. The max process stuff is memory that's assigned at startup, so that is restarting the machine. The queries per operation is a thing that can be set at session level, so you just have to reload the config. There are various rules of thumb, but again, those depend on what levels of concurrency you're expecting on your system. There's a trade-off around managing to run individual queries faster, but then you, at the extreme of that, effectively end up with one query consuming the entire machine, and then the next one, and then the next one. So it's a behavioral thing. This starts to look a little more like tuning big data warehouse appliances once those numbers get big enough. So you'll see them in the explain in this sort of form. There aren't always parallel workers available because we've set those maximums. So the planner may reach a conclusion that there should be, that this query could usefully be parallelized. So you'll see the work as planned, but you may not see them launched. And then you'll see these partial aggregates. Yeah? So if we're doing count star, fine, drop the table up into 5 bits, scan 5, push the 5 totals together. Yeah, the fact that those two numbers are the same suggests that the parallel workers were available when the execution wanted them. Right, so then just quickly looking through the various settings things. We've spoken about shared buffers. We've spoken about effective cache size, which is the shared buffers plus however much we think we're going to get of the operating system's cache. We need to allocate some memory for the sorts, the hashes, all that fun stuff, and potentially more memory for things that we know are memory intensive and will benefit from that, like vacuum operations. I mean, this is less of an issue from 18 onwards because of the more compact storage of that intermediate data for vacuum. So the vacuum process starts by going through the heap table. It collects up a list of dead records, and then it goes and scrubs those out of the indexes. That's really the reason why vacuum has to be there, so that we can keep the indexes and the body of the table in sync, that we don't have entries in the index pointing to records that aren't there or that now contain the wrong data in the table because B-tree index retrievals are not rechecked. Go get me this record. It gets the record. So that's why the storage of that was historically just essentially a big list. In 17, it was reworked into a radix tree, so we can now get a lot more identifiers for dead records into the same amount of memory. So maintenance work mem for vacuum is not as important now. Things like create index, they're big sorts. You want to keep that in memory. There's some real value to that. Yes, absolutely. I mean, because one of the reasons it's going to take a long time is that sort spills to disk. Yeah. If you are. Yeah, absolutely. I've seen some patterns where organizations will destroy indexes, do bulk loads or bulk update operations, and then recreate them. Yeah, those sorts of things. Yes, you can plan them, give it a lot more memory. If you're really running into trouble, that may again be a reason that you may want to partition, so that the amount of data you're trying to sort per partition comes down. I think this is stuff we all know. We've spoken about it, but already today. There are dead records. Nobody likes them. This is the stick everyone wants to beat Postgres with. So auto vacuum is your Roomba. It's been on by default for a very long time. Triggers for a table, so there's a certain number of auto vacuum workers. Once they finish a task, they will sleep for a period. That's one of the things you can configure. And then come back and start looking through the catalog for what the next thing is to vacuum. If you have a database that has only 1 or 2 very active tables, and you have a lot of cores, one of the things you may want to do is partition those tables so that you can vacuum multiple partitions at the same time. I'd argue that for that top statement, but yes. No, for bigger tables, you probably want to bring that 0.2 down. Yeah, very much about the environment. If you're ending up with I/O contention, or if you have a machine with a lot of cores and you start yourself additional processes, you certainly want to start changing some of those numbers. So yeah, there is an estimate in pgstat user tables. The plans that update or the plans that delete, the estimated row counts go in there. So if your stats are off, those numbers are going to go a bit weird. Here we go. For large tables, 20% is too long to wait. Yes. So what's large? Don't know. Yes, you do want to bring that number down. For the really big stuff, thresholds. Also for tables that have small active tails and very big stable piles of records at the top, these numbers really need to come down, or you're just never going to auto-vacuum. You can also manage the impact of this thing. So increase the amount of time between when the worker goes and looks for data again. This is not also set per database. You can set some of the stuff at a table level. So if you have tables that you want looked at more frequently, where you know all the trouble happens, you can set the number down. That vacuuming is an issue. So if it's getting really bad, you realize that the size of your database on disk is just ridiculous. Like I've only got 2 teras of data. Why am I consuming 40 teras of disk? But in the shorter term, you will start to see query performance degrade because if you're sequentially scanning, you're going past a whole bunch of records that are useless. It also does leave the indexes bloated because you have multiple copies of the pointers to every version of the record. So that query is a good start. How many dead tuples are estimated in each table? If you vacuum analyze, the reason to do those two operations together are you're reading the table anyway. So this is the other reason to do vacuum, but it's not really a big deal these days.
He did it last year. So.
On versions of Postgres past 14. Yeah. So there's far more careful use of transaction IDs. A lot of the read-only stuff doesn't end up with permanent transaction IDs in newer Postgres, so you're a lot less likely to hit this limit. If you wrap around, you're done. So one of the things that's done during vacuum as well is to mark records as frozen. So their visibility is not controlled by the transaction ID on that record. It is controlled by just this one is now visible to every currently running backend, and therefore to every backend in the future. So this is how we avoid the wraparound. So freeze max age. How do we scale? Right, we were talking about read replicas earlier. Some of the fun we can have there around replication. Vertical scaling, it's easy. Your Dell salesman will love you. More NVMe, more memory. 2 of those 96 core chips, great. But obviously, limits exist. Financial limits, the limits of what we can cool in any sensible data center, etc. A lot of this horizontal scaling stuff. So yes, partitioning gets us part of the way. In terms of we can parallelize scans better, we can get some of those maintenance operations running on smaller windows, because some of those maintenance operations, they're not sort of big O N, they're big O N squared or something like that. They get really, really difficult. I mentioned it earlier, very briefly. There are options for planning queries so two partitions that share a partitioning range are planned together. When we're talking about things like hash joins, that's very useful. But it does cause a complexity explosion in the query plan, which has not been fully fixed yet. So you can see your planning times blow out. It's worth looking at, though. If you have those kinds of workloads where you could really shrink down, particularly join operations, to get sort of the two partitions coming together. Sharding, there are no built-in solutions. There are a whole lot of forks of Postgres that shard in all sorts of interesting ways with different sort of outcomes. Your cituses, your timescales are great for just parallelizing massive ingests. Your warehouse PGs, your Cloudberries are all about planning the movement of data for big OLAP queries. So how do you reshard the stuff mid-query in order to deliver the best overall performance for the query? And that is a very, very hard, well, I say reshard. How do you move around the intermediate results in the best possible way to get the right query execution? It's a very hard problem. Right. I think we probably all get this. You write to one place, you read from others, as long as your reads aren't getting in the way of those things staying up to date.
That's something that coming from MySQL land, replica can apply the replication without read operations. Each other, and that was like blue line, and so that's
yeah.
You make your replica busy enough, you can slow down replication just because the same tables are being.
Yeah, but that has to do with the fact that the Postgres physical replication is actual physical blocks, whereas the MySQL replication is not. It's logical-ish. So connection pooling, we discussed this briefly earlier as well. This is really just about avoiding thrashing your server. You can go all the way down the complexity route to letting your proxy figure out what's a read and what's a write, and do all of that config. Or you can, if you have a simple enough workload, just stop the thrashing. There's a whole range of options there. So yeah, so one of the things that has improved a bit over time is the partitioning syntax. You no longer have to do all the explicit inheritance and all the rest of it. So create a table as partition of another table, give it a range of values. Talked about that. Right, where config lives. So there are a couple of virtual settings that you can have a look at in your Postgres PSQL command to tell you where the configuration is coming from. Generally, PostgreSQL.conf, pghba.conf, they live in the data directory by default. So the configuration for the whole server, including whether this thing's a replica and where it's getting its primary data from, is in PostgreSconf. PGHBA, host-based access, it's how you authenticate users. So we can read all of them. There is this virtual view, PG settings. So it's not just that you can get them with a show command in a shell. You can also write scripts to go have a look at them. Context tells you where you need to change them. There is also another setting on the end there around who can change them. Some of them only super users can change. including certain things that apply at session level. So as the Postgres user, you could alter user something set, and they may then not be able to change it back. Some of the memory settings like that, for instance. There are, two things here. You reload or you restart. There is in that PG settings system view a column around what state the setting is in at the moment, and it'll show you whether you are pending restart. In which case this is something you're going to have to bounce the server for. There is also an override for PostgreSconf. There's a file called Postgres autoconf, which is maintained through the alter system command. So it really is just an append-only thing. Last write wins. That's the reason it's in a separate file, because doing that in your main config file would get horrifically messy. Yes, this is the overwrite. After that's been processed, auto is processed. There are a number of, so one of the things about the nature of a particular setting is that it may not be modifiable through alter system. Okay. Right. I get to go on to our last set of slides. Excellent. Have? Oh, left it. Come on. Minutes. Cool. All right. Query tuning. Right. Our friend explain. What is my query going to do? Gives you it's not so much an execution plan as a data flow plan. Because the thing you see right at the top is the last thing that's going to happen. All the results flow up to that. You can do various options. So just seeing the plan is the first thing. This is where you'll see things like all the cardinality estimates, how many records are going to come through. That is one of the big killers of query performance, is that the inappropriate optimizations are applied because those numbers don't match. So you end up with nested loop joins instead of hash joins because the numbers look too small. You end up blowing out of memory and spilling all your hashing operations to disk because the number's too big. Explain analyze gives you what actually happened, runs the query, and then says, okay, this is what I guessed. These are the actual numbers. You can add a few other bits and pieces into that. You can get information about the buffers. There is also a JSON and a text output. So if you want to process these things with some sort of script, if that's something you want to spend your time building, there is a JSON output. Yes, text, JSON, YAML. Let's move on. Right, so this is all about cost estimates. And then you'll see the real values later if you run analyze. So cost is not a real number. It is compared to reading a single sequential page out of a sequential file. How expensive is this thing? That's just the unit that the gizmo works in. So we see a startup cost. So what is it going to cost to get to starting this step? So as you read up the plan in the text output, those startup cost numbers go up. What has to complete first before this can start? So you may see, for instance, multiple sequential scans with the startup cost of 0 because they'll start at the beginning of the query execution if you have parallel workers Then, okay, what is the cost at the end of this? How many rows are expected? And how big are the rows expected to be? This, on your sequential scans, reflects statistics around mainly the values in the variable length fields. So, yeah, if you have a lot of varchars, there is something done there based on the most frequent values, etc. How wide do we think these things are going to be? And that feeds into the cost of, okay, how many pages do we think we're going to have? Explain, analyze, gives us the real numbers. In our example here, we see estimated 110, got 111. So things are working the way they should be working. Our buffers, yeah, about a quarter of them were, about a quarter of the pages here came out of shared buffers, and then there was a certain amount of I/O that had to happen. Cool. Explain, analyze doesn't only apply to selects. You can explain, analyze other things. Put it inside a transaction. Footguns are available. Yeah, so that is an important one. There are some reasons to, this is a trivial example, but if you're doing updates based on big joins, it can still be quite interesting to see. But you do want to wrap them in transactions. So buffers, this is the one that is on by default in the more recent versions. Those are the buffers. Shared hit, how many things came out of cache. If it came out of the Postgres cache, we don't know what happened at the operating system level. So looking at the kind of nodes we're going to see in those plans, sequential scan is quite easy. Just run down the table. Index scan, look at the first entry in the index, go fetch the relevant pages. Look at the next entry in the index, go fetch the relevant pages. You'll often see this on the smaller, or the estimated to be smaller, size of a join. A variant on index scans and sequential scans is what is called the bitmap scan. So there we have multiple criteria on the table. You may see this as a result of a join on table you're filtering. You may see it as a result of having put multiple criteria on the records you want to return from a particular table. The indexes are compared, and the pages in the table that are in common among the 2 or the 3 or the 4 are then read back and scanned. So it's a way of reducing the number of pages that are read out of the table at the end of an index scan, because you do all the index work first and you only go fetch the stuff that overlaps. Obviously, there has to be things like logical AND operations to make that practical. Parallel scans, yep, we can go do parallel scans. Index only scan is what I was talking about earlier with the covering indexes under certain conditions. If we have all the pages that those records are on are marked as fully visible, so we know they aren't currently being changed, we can then just use the extra fields from the end of the index pages, and we don't have to go fetch the pages from the table. That is reliant, that full visibility thing, the visibility map, is reliant on those tables being quite well vacuumed. All right, we've talked about sequential scans. All righty. And then we see the join types. So nested loop is a simple one. For record 1 in the table on the left, go find me the record on the right. For record 2, go find me the record on the right, etc. This is often where you'll see index scans used. So go down the bigger set and go and fetch the relevant records. We also end up sorting. So we get information and explain about which fields are being sorted on, and then the method will tell us whether we are spilling to disk, and whether we are actually sorting the results, or whether we're achieving a sorted result by going down an index and fetching the relevant records for each value in the index. Sort, yes. Yeah, so there we go. External merge. You've spilt out, you've gone stuck a bunch of stuff on disk. Oh, I'm up there. Okay. So pgstat statements is one of those things we can use to find our problematic queries. It works by creating signatures for queries. So it takes out the particular values for any of the literals or any of the fields in there, and creates a signature for the shape of the query. I'm reading this table, filtering on the following field, and then you can see how many of those have run, what their average time is, etc., etc. And there are two ways you can look at this. One of them is, of course, which queries are individually running slowest, but that's not always the most interesting if they're running very infrequently. So the queries by total time spent executing may be a bit more interesting. We also know how much I/O there is. So as we saw in explain, we could get the number of blocks. pgstat statements will log the number of blocks for us. This is part of the reason that pgstat statements is not in by default, because as we turn on more of these options, as we start tracking more and more of these things, there's just more overhead. There's more, locking of the counters, all of that sort of stuff that goes on in the background. Also, at some point, you can just reset all of them. So if you make changes, you reset. If you are using tools like the Postgres Workload Analyzer, you may opt to reset them every time you export them as well, rather than just leave them accumulating. So then you'll, sorry? Probably. So one of the other things you can do, if you're willing to put up with some overhead, to go along with your slow query logs. So when we looked at logging, we looked at the logman duration. So how long does a query need to run before we're going to log it? We can also grab its explain plan. Okay, we have a slow query. What did it actually think it was doing?
So that's not.
No, it's not.
Hopefully, what was happening at the time.
Yes. So they are two separate operations. It is not the plan that was used to execute the slow query. It is annoyingly. Again, that's also an instrumentation question. To get there, you'd need to be watching all those hooks for every single query that runs. It's a hard sell. Yeah, a lot of the debate around some of these features in the Postgres community comes down to what's it going to do to users who aren't actually using the feature? How much worse is it going to make their lives? And pulling out explain analyze for every query that runs is going to make everyone's life really a whole lot slower. So it is a two-part operation. Okay, this query ran slow. Cool. Take the query, replan it.
Hopefully.
Which most of the time is close enough, yes. Yeah.
We tried it for last year.
Yeah?
It help us. Almost never gave us the bad plan.
Almost never.
Almost.
As long as it wasn't actually never, yeah. Okay, yeah, so just a quick exercise on auto-explain. I mean, this is probably going to be a far bigger number than your log than your log min duration. So auto-explain has its own min duration setting, and that will probably be a whole lot bigger than your log min duration in the practical world. You're not going to auto-explain everything. You're going to only auto-explain the far edge. Okay. Yeah. So our auto-explain management. So this is the duration. Run it in a transaction. So try to rerun it. Do we show the IO statistics? And are we logging plans inside functions? So nested statements. By default, that is off. All right. Now we get to indexing. Who loves indexes? Yeah. So simple answer. All right, B-tree. Yeah, basic implementation. So we can do equality. We can do greater than, less than. Basic ordering stuff. You may want to build a multi-column one because you're querying data together. You may also only care about optimizing certain queries because maintaining these indexes is expensive. It amplifies I/O. The more indexes you have, the longer it's going to take your vacuum jobs to complete. So there are reasons potentially not to have them. There may be only certain queries that you care about. Yeah, so, for instance, you only index the currently open jobs. Once the jobs are closed, we can go scanning more slowly because they're not part of the active experience. And that's where you'd end up with a partial index. So you put a predicate into the construction of the index. We've spoken a little bit about the covering indexes, mainly used on B-tree indexes. You can get them on GISTs as well, but you can't get them on GINs. Thing your index also doesn't have to be a field. It can be an expression. So you can run some kind of function and use that thing as the value in the index. Obviously, that only makes sense when that's something you use in the query. Probably makes a bit more sense if it is something that's quite computationally expensive. Yeah. But so instead of looking up the record and doing the calculation, you can just go looking for that value. Again, it has to be something you're doing as a predicate for that to make sense. Then there are various indexing frameworks that are used in Postgres. This really starts to show some of Postgres's academic history, that all these things got built. So Gin is great for bits of objects. So some of the text stuff like the trigrams are built on Gin. The indexing for JSON data types is built on Gin. Gist is more useful for ideas of containment. So a lot of the spatial stuff is built on the back of Gist, and some things like some of the alternate full text search things. Brin, one that I quite like coming from the data warehouse world. It is a range of values for particularly numeric values most of the time for certain ranges of tables. So you say, I'm looking for all orders placed in 2022. We don't need to index the year column. We just, for every set of pages, and it's normally not one, I think by default it's 10. okay, what's the min and the max of this in that range? So for things that have natural order, it gets very efficient. For things that have natural order, like timing, you can actually stretch that number of blocks quite a lot, and you can very cheaply find the right blocks to work with. So they're small, they're cheap to maintain, but they'll still give you a lot of those gains, particularly for OLAP type workloads, but not only. HNSW is the hierarchical navigable small world that is the preferred kind of vector similarity search, vector similarity index. We don't have time to go through the doodle, but yes, it's quite an interesting idea. It's a skip scan style model for high dimensionality data, not common dimensionality. Okay, spoken about that. Yes. So you will see bitmap index scan when you're using the B-tree indexes. So if we use the standard TS vector built-in text search, that is built on the back of a GIN index. So you'll view that again. It comes down to a bitmap scan. So the GIN index returns the following ranges of pages need to be scanned in order to find the answer. Of course, there's a PostGIS example for GIST. Oh, so I think we covered that one. So composite types, composite indexes. You can use the earlier columns in a composite index on their own in a predicate and still use the index. You can't use the later ones on their own. I mean, that's a fairly standard thing about the construction of a B-tree index. It's going to be the same everywhere. Include, so this is the syntax for the covering indexes. Build an index on one field and add a few other things into the index structure so that you don't have to go and retrieve all the data. Partials, expressions, we've talked about all of these. Very briefly, when not to index, columns are too small, you don't use them often enough. Very few distinct values. You may want to use something like a BRIN if they are distributed over time. Let's say you have seasonal markers, summer, winter. You could find big blocks of them that match that even if you've only got a few values. A full B tree is not worth the issue. And it mainly comes down to maintenance cost. Maintaining indexes is expensive at write time. It's expensive at vacuum time. Yeah, indexing those is very unlikely to be worth the effort. Right then, thank you very much. If that was